Professor Eileen Martin, who's joining us via Zoom. So can you please help with the switch? And I'll do the introduction in the meantime. So Professor Eileen Martin is an assistant professor of geophysics and applied math at Colorado School of Mines. She holds a PhD in computational mathematical engineering, a master's degree in geophysics, and a bachelor degrees in mathematics and computational physics. Her work in computational geophysics has been recognized by the National Science Foundation Career Grant and the SIAM Activity Group on Geosciences Early Career Prize. The topic that she's going to be presenting couldn't have been more pressing in our context. You've all been shaken out of your beds with the recent earthquakes with an S. And I think it's about time for us to hear from scientists what is it that they're dealing with in terms of data, in terms of also risk assessment, probably not prediction, but she's going to tell us all about it. Of course, this has to be bracketed. We know that our Earth Sciences or the geology program has switched to an Earth Science program, and hopefully in the years to come, there will be local speakers also joining and speaking about the topic from our local context. Eileen will be speaking today about the advent of these fiber optic telecommunication networks that allow to collect seismic data that are close to urban areas and can improve earthquake hazard tools. However, these data are collected at such fast rate and with such high resolution that humans cannot inspect it manually. So in this talk, Eileen will discuss several examples of how the use of machine learning techniques is put to action to understand and assist humans in processing these big data, and how we're using machine learning to ensure people's privacy is protected in areas where these data are collected. So please help me in welcoming Professor Eileen. Eileen, the floor is yours.
Thank you. And thank you so much for letting me join remotely. I'm going to be talking about some case studies in the United States, but I also would like to highlight some work that's going on currently in Istanbul, Turkey, led by my collaborator and colleague at Colorado School of Mines, Ebru Bozdag. She's been collecting seismic data throughout the city of Istanbul at high density continuously for a couple of months now. And so I hope that perhaps in the near future, she may also be a speaker that you would be interested in interacting with. But let's look big picture at how data science is sort of transforming this space of urban geophysics, and especially urban seismology and earthquake hazard science. So as we look into even the near past, a decade back and beyond, geophysics has primarily been done only in relatively quiet places. This is a photo I took at one of my field sites up in Utqiagvik, Alaska, the farthest north town in the United States. And the loudest sounds that we get are things like a goose walking around close to our sensors, or sea ice scraping along in the winter nearby. This is a quiet place. This allows us to get very good high quality readings of seismic vibrations in the ground, but it's not close to where there's a large urban center. And there's an increasingly large proportion of the Earth's population living in urban centers. And so I'm going to talk about some technologies that are allowing us to get into urban centers and bring geophysics close to where people are. But of course, people are much smaller than seismic waves and earthquake vibrations. And so this means that we need to have really high density sensors. Luckily, over the past couple of decades, there have been huge advances in the types of seismic sensors that we can use. This ranges from things like low-powered wireless node networks, like what's being used in Groningen in the Netherlands to deal with induced seismicity earthquakes, things like cell phone accelerometers, which are being used in California to enhance the early earthquake warning networks, things like nimble nodes or nodal arrays. These are lower-cost seismometers in the sort of traditional sense. And the technology that I work with most frequently is called distributed acoustic sensing. This takes a standard single mode telecommunications fiber optic cable and repurposes it as an array of many, many seismic sensors just hooked up to a single power source. All of these different technologies are allowing us to have many more sensors with much higher sensor density over large areas. So what that means is when someone is walking around on, one block, and maybe there's a construction site on the next block, we do have the resolution in our data to be able to distinguish where those vibrations are coming from and whether they're a local noise or whether it's something like an earthquake wave that we really do care about and want to study. One of the reasons that I really like working with distributed acoustic sensing is that those fiber optic cables are already all over the place to support our telecommunications networks. It's a bit of a logistical challenge to be able to collaborate with either governmental or telecom industry partners to be able to get access to those cables. But each time that we overcome those hurdles, these become extremely easy seismic networks to maintain. For example, back in 2016, I got to work with Biondo Biondi and create one of the first urban seismic networks based on telecommunications infrastructures. And this array ran for 3 years continuously. We only had to do maintenance on it maybe twice. In contrast, traditional seismic networks require people to regularly go out every couple of months to check in on each one of the individual sensors. With this type of setup with our telecom infrastructure, we have one computer, one what we call optical interrogator unit that sits in a computer server room in one of the buildings in the city. And we just have to check in on that one point. And in fact, we can even remotely access it very easily, meaning that we don't even physically have to be on site to be able to maintain this earthquake network after those fiber optic cables are in the ground. And on the left and in the middle, you see a couple of examples of how those fiber optic cables are installed. When those cables are installed, they're typically over-installed by at least a factor of 2 to 3 beyond what the capacity is that's needed. And so telecom companies or government organizations that run these telecom networks are then able to rent out the remaining fiber optics within those cables that are not being used for telecom purposes. And we are able to purchase that time or get that time on loan from these organizations. This means that we're able to get a very large data set with relatively low effort and low cost. Why do we want to do this? Why do we want to bring our geophysics into urban areas? As you all know, earthquake hazards are incredibly important to understand. And this also is important in the planning phases. Before you have an earthquake, you want to be able to have very good, what we call earthquake microzonation. This tells you at a small scale whether different parts of a city need to have certain building codes or not. And so this is what we call earthquake hazard mapping. And as seismologists, the way that we inform what earthquake microzonation is by providing maps of the speed of wave propagation in the Earth's subsurface, and especially in the near surface, the top sort of 30 meters of the subsurface. And we provide that information, and that's actually how we interpret what types of soils or rocks our cities are built on top of. Ideally, we'd like to be able to do this microzonation so that it's on a block-to-block scale, which is a bit smaller than what happens right now. And we'd like to make sure that we have very reliable boundaries for where those regions are that need different types of reinforcement of buildings so that we can better inform retrofitting of buildings and things like that. But of course, there are other purposes for bringing geophysics into cities. And when we create these new seismic networks in cities, we want to make sure that they can help inform as many different applications as possible to bring a lot of value to the public. For example, we would also in the future like to be able to use these fiber optic sensors to help with early earthquake warning. And so I'm part of an effort with the US Geological Survey this year to explore what are the different ways that we can bring value to these areas in earthquake hazard response and figure out the feasibility of these types of applications. We might also be interested in things like groundwater monitoring in urban areas. Particularly in the Western US, we suffer from a lack of groundwater and drought conditions that have become exacerbated by climate change. And so ideally, we would like to be able to contribute to the ability to find groundwater and to monitor its suitability in areas close to where people are living. One of the biggest challenges that we run into, though, is that even though we can collect all of these data, not every city is the same. In fact, every single urban experiment that I've been part of has had quite a different set of data. And so on the far left, you can see a view of what our data look like. The vertical axis on the far left is what we call the channel. That's the distance along our fiber optic cable. And it's divided up into small segments, about 4 meters long. Each one of those acts as its own seismic sensor of vibrations and has a time series that's recorded. And on the horizontal axis, you can see that only 10 seconds of data are being shown here. I've labeled some places like a busy road, a car or vehicle driving by, a pop from a construction site that's in that area. And each location that we go to has some different characteristics to it. In the top middle, you see something that we call an earthquake or a spectra. And so what this is showing is 1 week of data recorded at one location. And you can see things like the Monday, Tuesday, Wednesday, Thursday, Friday vehicle patterns and noise patterns of people being at work in this location. And we can also see things like plumbing systems and heating and air conditioning systems that can help us understand efficiency of our buildings and our cities as well, potentially. Up on the top right is another location where there was sort of a more rural area extending out from the city of Sacramento, California, and we could see many trains going by. This was a study done by Lawrence Berkeley Lab. And in the bottom right, we see an example of a parade that was recorded by a group over at Caltech. And there are things like motorcycles going around, floats, and that sort of thing. And then in the bottom middle, we see a piece of noise that I'm going to talk about later, which is some footsteps that we could see in one of the arrays that was recorded at Penn State University. And of course, we want to make sure that when these types of things like footsteps that could potentially lead people to some personally identifiable information that residents may not be so comfortable with, we want to make sure that that is staying private and that we're able to sort of filter that out from our data sets. But being able to detect these different types of noises is a challenge. These are large data sets. We're collecting data at a faster rate than the seismology community has ever seen before outside of oil and gas exploration. On the far left, you see an example of the rates of data that are collected by the IRIS Data Management Center. In the US, this is our big academic seismology data archive. And you can see that over about 30 years period, they've collected something like 700 terabytes of data from all different sources, all the different seismology groups in the US over 3 decades. On the right, you see a collection of just 9 experiments that one of my collaborators and I just sort of chose at random, low data rates and high data rates over a 5-year period. And it already added up to almost 800 terabytes of data. So more data being generated by just a couple of research groups in a very short period of time than the entire United States seismology community over several decades. So this is a step change for the seismology community. And to put this into more perspective, kind of squished over the cumulative data from fiber optic experiments to be on the same time scale as the traditional seismology archive. And you can see that it's a much, much faster rate. So currently, it's difficult for us to share our data publicly. And in fact, this also leads to other issues, like if we were to be able to start to create automated processes using machine learning techniques to start to understand our urban geophysical data, and we wanted to try to label different windows of the data that we record, this wouldn't be feasible. So we went through an exercise in a working group that I'm part of, and we actually said, well, what if we tried to propose a program where we would actually create a database of different seismic noises or vibrations versus earthquakes and other events and tried to label those? What would this take? Well, today, the way that these sensors are growing, we're typically seeing something like 10,000 sensors per array. And if we were to take that and break it into just 250 sensor by 30-second blocks in time and try to look at each of these images of our data and label what are the events going on, And we just spent 15 seconds of reading those files, visualizing them, and labeling them manually for each one of those. It would take 84 weeks straight with 40 hours per week of work to label just 1 week of recorded data. So obviously, we have to really limit the amount of human inspection of this data. It has to be very automated. And in fact, we do have to rely much more on unsupervised learning techniques for this kind of analysis. To give you a little bit more of a feel of what we're doing with these data, I wanted to show you this case study that was one of the earliest, what we call dark fiber studies that was done at the Stanford campus. So on the left, you see the Stanford campus. It's not a true urban area, but it's at least suburban and quite busy. And the red line shows the route underground of where fiber optic cables are. None of these fiber optic cables are visible when you show up to campus. You would have no idea that they're there. They sit underground in that PVC pipe. That PVC pipe is sometimes cemented into place, and then it's about 1 to 2 meters below the surface of the earth. And of course, we have a great mix of materials, both man-made and natural, in this area, as well as any other urban area that you go to. You may also have old bits of material from old construction and things like that. And on the Stanford campus, this is also an interesting area because it's in California, which is an area with high seismic risk and quite a bit of earthquake activity. To put this in context for how earthquake hazard analysis has traditionally been done, on the right, you see an example of how a near-surface seismic survey was done in the past that helped to inform earthquake microzonation around this area. And I've overlaid this little square figure-8 shape of the array at scale with the other locations. So each one of these small blue lines is one point where there was one measurement taken. In the space of where we have that red figure-8 shape, which is our fiber optic array, there are 600 sensors spaced there. And so we're potentially able to get as many as 600 locations where we can get separate measurements of what our seismic wave speeds are, which then helps us to understand those materials and how our earthquake risk is going to work. So we're making this much higher density. Previously, you might have had, in a very high quality study like this, you might have had one location per 0.5 kilometer to 2 kilometers. Now suddenly we have one location per 4 meters. So a real step change on the data amounts. And we're able to see much, much more detailed responses to earthquakes in this area. So on the left is just an example of one earthquake in the same region, about 30 miles away, coming from Berkeley, California area, Piedmont, which was a magnitude 3.5 earthquake. That's large enough that you would feel it if you were nearby, but not particularly large and damaging, given that the buildings in California are generally following earthquake codes. On the right, though, you can see a very strong response on these fiber optic cables, which were just using telecommunications infrastructure. And you can see the arrival of what we call a P and an S wave. It was really exciting to us that we could see these P waves because those are an essential element in the types of early earthquake warning systems that we hope these cables are then going to be able to help us contribute to. One of the interesting things that we could see was the variability across different locations and how this response was. And in particular, between a couple of buildings, we got very high resonance whenever we would have vibrations from earthquakes or other man-made vibrations. And so that was very interesting to us that sort of the basements of these buildings were almost acting like a bell ringing. Additionally, we also have techniques that are quite data intensive on the computational side, but are possible, where we're able to use these continuously recorded low amplitude ambient seismic noise data, and we can in fact use those to directly image the Earth's subsurface, which is a key part of being able to do earthquake microzonation. So on the right, you see many different locations. You see about 9 locations along just a few hundred meters region where we were able to do seismic imaging and detect what what we call VS30 measurement is. And that's a key metric for being able to improve earthquake microzonation. one of the ways that we tried to improve this, because there are some theoretical considerations in how we use these ambient noise, is that we needed to remove vehicle noise from our data. And so we were able to develop a workflow where we use continuous wavelet transform features to respect the sort of spatial temporal characteristics of things. And we carried out a number of different clustering algorithms, including things like batch k-means and hierarchical agglomerative clustering with different distance metrics. And we were able to, in fact, identify patterns that corresponded to where we had more vehicle traffic. And we're able to separate out cars from other loud noises and, of course, from quieter noises as well. In fact, this helped us improve the convergence of our results so that we would not have to use quite as long data recordings to be able to start doing seismic imaging. But like I said, there's a challenge that every location is unique and varies quite substantially. And so it wasn't clear the extent to which all of those results would be able to carry over to every other urban area. I got involved with a project that my collaborator Tian Zhu was starting up at Penn State a few years later called the 4C Array. It's fiber optics for environmental sensing. It's over at Penn State on the eastern coast of the US. It's quite different, lower seismic risk, but quite a bit more saturation and flooding risk, a lot more questions about groundwater also and landslides in that eastern US area. So different concerns for geohazards, but relatively similar setup for how we were able to use fiber optic cables underground under a college campus. We were able to see different noises. On the top right, you can see a more fun example of a concert that had happened, and we could actually play back the bass lines of the bass guitars there. On the bottom, though, we were very surprised to see that we could get footsteps out of these data. And we know that to make smart cities a reality, it's important to get stakeholders like residents in the areas where you're trying to do sensing to be on board with this. And especially in the US, there's a lot of discomfort around surveillance of people in areas where they live and work. And so we wanted to make sure that people would be comfortable with these data being reported and potentially shared. And that means being able to remove footsteps from our data. So I got to work with a team of just undergraduates to create a neural network, just several layers deep, and fine tune it to get reasonably good performance, about 85%, on being able to detect whether we have footsteps in an area or not, so that we can then randomly remove those footsteps from the data, depending on whether we see them or not. And so for us, it's really important that we're able to make people comfortable, because these systems are not going to be a reality and are not going to have that impact that they need to have if people are uncomfortable with having the data recorded in the first place. One of the other things we've been doing is looking to other application areas that need to have sort of high density sensing with the same types of sensors to be able to improve or to look for different features that are useful for our event classifications. And so one example of this was looking at an experiment on Rhona Glacier in the Swiss Alps. It's a glacier that has many different seismic events going on, and we were able to come up with a whole array of other features, such as the coherency between our sensors, their eigenvalue decay of those matrices, looking at things like FK transforms and tau P transforms that tell us how fast and how coherent waves are in local regions, to be able to detect and classify different types of seismic events happening throughout the entire glacier over time. Here's a few examples of those different categories of events on the glacier. And so these types of features are actually also useful for us in urban seismic data. So just to wrap up and summarize, we're finding that seismic data acquisition in cities is getting easier. This is both on the side of the sensors, as well as being able to use things like just our randomly generated noise, like our sources. Geophysics in cities is really important to be able to help us have resilient infrastructure, to be prepared for hazards, and to be able to plan what we need to do in our building codes for that, and also for things like environmental monitoring. But it's only going to happen with high density sensors so that we can distinguish the noises that people make and that we don't necessarily care about from the noises that are the ones we really care about, the geophysical signals. And so data science techniques are really critical to being able to analyze these high density data that are continuously recorded and to characterize these signals in cities so that we can overcome different challenges with our variability in our data, our differences in our cities over time, those changing noises that might happen, and also to be able to ensure resident privacy so that we can actually make smart cities a reality. I'd like to acknowledge a few different collaborators on this work. I am really blessed to have many different collaborators across computational science and geophysics, and so would like to recognize their contributions to the results that I've shown in this talk. Thank you.
Okay, thank you. Thank you, Eileen. I think I'm going to be the very brutal moderator and allow just for a question which was in the chat. Again, we're relying on our friends and the speakers to, accommodate us for the longer discussions with the crowd tomorrow. So we apologize if we're, cutting the time for the questions. So there's just this one question about the cost of these technologies. Is it going to be the main hurdle in adopting such technologies in data acquisition?
Yeah, this is a great question. So on the fiber optic cables themselves, they range from about $1 per meter to $10 per meter. For the standard telecom cables that we would use in cities, that's going to be closer to the $1 per meter range. And so that means about $1 per sensor. In contrast, if I look at a seismic node array, those are approximately $1,500 per sensor. And so $1 per additional sensor versus $1,500 per additional sensor. But there's a caveat. The optical interrogator unit, which is the computer and the optoelectronics and lasers that we use to actually make this measurement along many sensors along that fiber optic cable, that optical interrogator unit is one purchase that you have to make that's quite large. It can range from 100,000 up to a couple of 100,000, depending on what your needs are for the experiment, what the distance is that you'd like to cover. And so that's a big purchase. Luckily, you don't need to have it plugged into the same cable all the time. You could move around the same interrogator for many different experiments, an entire country. If they wanted to be very aggressive about improving their earthquake microzonation, could use one interrogator, plug into fiber optic networks throughout the whole area and just make that purchase once. Within the US and our National Science Foundation facilities, I am helping to push for having wider availability and free use to people that are able to get funding through those organizations for projects so that they are not having to make those purchases themselves. And it's certainly a science equity issue to make sure that those optical interrogator units are available at low cost or even free to scientists who want to do these kinds of safety and environment focused problems.
Okay, thank you, Eileen. And I guess tomorrow we'll have the more extended talk and exchange with the crowd. So thank you so much for joining.
Looking forward to it. Thank you.
And